So the last one is a density-based approach, as opposed to this kind of putting these into partitions. We're going to say, what do we use the density of the data itself? So one thing about K-means as well is that, and this, somebody was asking a question about this yesterday, I think, is like that K-means essentially grows circular ovoid distances. Like in my drawings, I was doing very like wraparound things, but actually if you think about the distance, it's going to be kind of an ellipse, right, of some kind, a cloud of points. Because if you're really closer, outside that ellipse, you might be closer to a different centroid. So K-means is not going to be very good at a data set like this, where we've got data points that are in multiple clusters that wrap around each other, and it's important to get those curvatures properly, right? So we need something that handles local structure a bit better. So the coolest, simplest one in this area that's easy to use is DBScan, and it uses a bit more complex distance neighborhood idea, but not really that bad. So DBScan, what do? We give it our data points x. Sorry, it happens whenever I switch between pen and mouse. Our data points x are m points, right? So we're going to have neighborhoods, right? So we're going to talk about neighborhoods with Canadian spelling, and we're going to say a neighborhood is defined by a distance from point and a number of neighbors, right? And so a data point, if this is our current data point, a data point has a distance epsilon, which is a space around it, which is its core group of friends or local points, and then a number of neighbors, m, which is to say that for them to be in the same group, you have to have at least m in there, right? And so we're going to call a point core if relative to the current query point, right? So we go through for every data point xi, we can compute its core points, its border points, and its noise points, right? For each cluster. No, it has to be relative to each point. So for this point, we're going to say, we just look at the neighbors around us. We have to compute distances between points again, so that's unavoidable. But if we have, if this point has at least m neighbors, and so at this point we're saying, let's say m equals 3 in this example, and epsilon is this distance. If they have 3 neighbors and they're all within epsilon, then they're going to all be core points of this guy, and so they're basically in the same cluster. And by the same measure then, when he's the center, we'd compute their core points and figure out if they're in the same cluster, right? But once you decide something's in the same cluster or not, it has to be consistent across all the points. And then a border point are going to be points that are neighbors of that if you have a point that right, so from this guy's point of view, if he's the x, this is epsilon, right? He has one neighbor within that distance, but only one, so he hasn't met the threshold for the number of neighbors, and so he's considered just a border point for this guy. I guess a better way to think of it as that if he's the this point's the center point that we're looking at, what are the parts in its class, right? And so this blue point here doesn't satisfy that it's in a neighborhood of m, and so it only has that as a border point. And then noise points are points that don't satisfy either of these criteria. There's no point within epsilon, not even m of them, and so they're on their own. So we can basically use these rules to come up with, for every data point, what its core, border, and noise points are, and then we could color them using these colors. And so originally, if our data set is this, and we use that approach on every data point and compute its core, border, and noise, and just say core is one color, right? So core is core, this is the first phase of it, then we'd get this coloring. So hopefully everybody can see the colors on this as well. I'll zoom in a little bit so it's more visible. Right, and so all these, if a point is red, that means that from its point of view, it's an edge node that doesn't have any neighbors that are close enough. All these blue points have neighbors within the epsilon distance, but not m of them, not 3. And all the green ones have 3 neighbors within that distance or more, and they're all happy, right? And so we do that, and we get this now first level breakdown of the points where now I've wrecked it. Ah, okay, that's what I'm doing wrong. Sorry. We get this breakdown of the points where we at least know if all the points are core or not. And then in this one we were using minimum points, so m to be 4 and the epsilon to be 10, I guess, in the data set that we had for it. And once you have these clusters now, essentially, it's determined. In this case, we didn't have to say k, right? So the number of clusters did not have to be specified because it automatically found these groupings. And so we can do some kind of simple scan of like distances and just do like a minimum spanning tree or find points and say any points that are core, if their distances are beyond some higher level, then we stop. All right, so if we do a very simple agglomerative clustering on this, we would end up getting this clustering where all the points that are core and don't have any obvious gap between them, because this gap is so big relative to the other ones that these would be split last. So there'd be some easy threshold on an agglomerative approach where you'd come up with these classes, and now you've got a really nice complex structure of classes that have like wraparound effects, and you didn't even have to specify k, right? Because it automatically figured it out. And you've also got an outlier detector because all these points are just kind of weird and didn't really fit into any class. I mean, you could argue maybe they should, but for some reason, yeah, so I guess in that case, right, we had a small set of points here that were in a cluster, but they're on their own, so you'd have to decide how many points you need in a cluster as well. So DBScan gives you a first pass that lets you do that, but then you still have to figure out what to do next. And so I'll just finish off on DBScan. Here's just 2 more slides, and I'll go back and answer some other questions. So again, just like Kmeans, DBScan isn't always the best choice, but it works well in certain situations, right? So the data set we saw before, that's really good if the structure of the points is really mixed. So in this case, are we saying this is good or bad? In this case, if you're talking about doing Kmeans, you probably would come up with something like this, which seems good for certain data points. Right, so this looks like a Kmeans clustering of it. If I said that you have to have k equals 6, I'm not sure if that really fits exactly, I guess. They could be overlapping. Yeah. And k equals 6, then you might get this, and it works fine for these classes, but it's really not very good for this area, because why are these ones separate? I'm not even sure if you would get this exactly with Kmeans, because the overlapping would be complicated. Yeah, no, because these would be out there. So this is just an idea, I guess. Trying to remember from where we got this, what we meant. That maybe this is what the true clustering should be. So ignore that, because these are very dense, even though they are all together. So, oh, okay, no, I remember. If you did Kmeans of 3, right, you might expect to get that, right, where you're saying, oh, these guys are all just near each other, and your means would be these, right? And it can't handle this density part, they'd all just be together. And so for DBScan, you can get different settings of it. The problem now is we don't have to say how many clusters we need, but we do have to say what's a neighborhood, right? So what's the density you want? So if we say a neighborhood has 4 points in it and it must be this distance, we'd get this clustering, which is essentially the same as the K-means one. But if we had a higher, change the distance a little bit, now all these points become outliers because they're too far from each other, but we get those sub-areas really well. Right, so the fact of it just might be that you might have to try like running different algorithms to handle different sets of data points and then you remove them, right? Because say you did it this way, these data points now are all left out. You could essentially remove these ones from your set and then do clustering again on the remainder part. I'm not sure what people do when they're really trying to do a lot of clustering, but you can mix and match the different methods. But it's not always going to work that well, is the point. It's really good for, say, this kind of data set, where there's really two types of density, right? There's dense and there's sparse, right? And you're really trying to find two different levels. But then there could be multiple classes of dense, right? And you have to specify what the density is. So you're given it one type of parameter for another. It's good for finding shapes. It's good for handling essentially two different levels of density, but not a lot of other ones. If you have, I guess, a lot of very dense points that have lots of large neighborhoods, the calculations get expensive, but it's a bit cheaper than K-means in terms of the overall calculation. So we had some other questions about related things. And maybe I'll go back to that overview slide we had here. So that's what you're asking. So averaging, so running K-means multiple times, yeah, you have to, deciding the right way to combine them, you have to make sure it makes sense, right? You can't just average the answers, right? Because every point does have to be in a set. So in a way, you could do multiple runs and have them vote, essentially, like should this pair of points be in the same cluster or not, right? And if they're voted to be in the same cluster many times, then that would be a way to do it. But it might also be that you'd run it many times and then have some other metric that says, is this a good evaluation of clusters? And so the videos you can look on YouTube next to cover a few things on that. And so you could basically run K-means a bunch of times and then pick the one that maximizes the metric that you're using and does that. So this week's playlist, and I'll make sure everybody does this. We go to our class and we have the this week playlist. Yesterday's support vector machines there, but this one on evaluation measures. There's a bunch of methods, essentially using some of the same ideas we have, like a confusion matrix for counting correct and incorrect matches, but then using that to evaluate the clusters. So it could be that someone gives you some labels just for the purpose of evaluation, so you can do a supervised kind of error analysis, or you can have an unsupervised one that looks at these metrics of density and sparsity of the points and saying, is it really a good clustering? And so that would be the way probably the best way to combine it once you do multiple runs from K-means, trying to pick the ones that is the best setting. Because merging them, yeah, you can't just average it, right? Because which point do they go to? You can try to fuse them in some way. I'm sure there's approaches people use for that. But I think the best way is really to pick ones that that maximize your score and say, well, here's a good clustering we found, right? For the initialization and it being sensitive to those first points still on K-means, it won't necessarily converge to the same solution. For a given K and any initialization, would we always converge to the same solution? Given K. I mean, for the particular, it depends on your computer and your algorithm, I guess. Does it? No. So if you give it the same K and the same starting points, it's deterministic because you're just computing the averages, right? So if you choose the exact same starting points and the same k, yes, you should get the exact same solution every time. But if you're sampling randomly what your starting points are, then you would get a different solution every time, even for the same k. So it's not even conversion to the same class, same clustering, just for the same k. But yeah, if you set the starting points to be the same, it'll give you the same amount because there's no randomness in this after you chose the starting points. CAPTCHAs. I guess somebody's asking about CAPTCHAs for DBScan because it kind of looks like human text. Is that the idea? If that's the question, I would say no. CAPTCHAs these days have moved onto a so I mean you could use it to try to classify, to extract out strokes of like handwriting and stuff, I guess. But these days, for that kind of thing, people use convolutional neural networks and lots of other stuff, because trying to understand human writing, the random scribbles, you're not just trying to find where the lines are from the points, but you're trying to find out what the character is and is it similar to other characters. But usually that's a supervised state because you do know what the right answers are. But you could do clustering on that as well, I guess, with CNNs. When we talk about CNNs, we'll talk about that. But not as far as I know. You could use this for the initial extraction of strokes and points and pixels to figure out what's the noise and all the random little, spots when you're writing something, and get rid of all this junk. So you could use it to clean up. So clustering, one of the big applications people talk about is denoising, right? So in that sense, that is a popular thing because you can basically now just get rid of all these noise points and say, here's the core strokes or lines in your data set. Cool. Okay, so I'm going to end there. We went through clustering unsupervised methods, and if people have questions, feel free to post them online, and I will post this video up on YouTube by this evening. And then next week we'll talk about anomaly detection, which is kind of another subset of unsupervised learning where you're trying to find really just the outliers or just the strange points and trying to detect them because they might be an error or a safety issue or something. But let's, we can reconvene for if you have other questions for the office hours tomorrow and have questions about the test or other topics we talked about in class. But take a look at the assignment and make sure there's everything in it kind of makes some sense, and we'll get that started for everybody. So thanks for coming. Have a nice day and a nice week if we don't see you tomorrow. Bye for now.